field cost infinite. So that means it doesn't. That means it's impossible. So for generator 1, the range is from 50 to 200. Okay. So based on this column and this column, you have the input-output curve for generator 1. It's a multiple linear segment, and the operating range is from 50 to 200. Okay. So you continue for generator 2. This is the field cost for generator 2. Okay. For generator 2, when the power is 0, the field cost infinite. For 50 is 750. Okay, you continue like this. And you found that when it's 175, the field cost is infinite. So for P2, the range is from 50 to 150. Okay. Similar for P3, you can find that the minimum is 50 and maximum is 175. Okay. So based on table, we can get this information. Okay. We also found that the step size is 25. Okay, the step size 25. 50, 75, 125. So the step size is 25. However, we have a total load of 310. That means 300 plus 10. Okay. This 300 can be divided by 25, but this can't be divided by 25. So that means this 10 should be properly allocated between these three generators. Okay. That means the load doesn't fit data exactly. Interpolation is needed between the available cost value, closest value 300 and 325. Can easily calculate 300, or we can easily calculate 325. But for 310, I have to handle it carefully, okay, because it's not doesn't it's the data, okay, because the step is 25, you see, okay. Let's continue. First, we give the we have to calculate the field cost for 2 generators. Okay, for these 3 generators, our problem is that we have to find the optimal solution to support the total load of 3 generators to support 310 megawatt to use 3 generators. First, we calculate how to allocate this the total generation between 2 generators. It's very similar like this. We have to travel from A to N. There are many stages. First, we calculate one stage, and then we add another stage, and then we add another stage, and then we add another stage. Finally, we calculate all the stages. Okay, this is the logic for dynamic programming to solve this mathematical problem. Okay. For our economic dispatch, our problem is that we have to find 3 generators. We have to find 3 generators to support this total load of 310 megawatt. First, we calculate 2 generators to support the total load. Then we calculate 3 generators to support the total load. Okay, it's in a similar way. That means first we use the just a few generators. Then we add 1 generator. Then we add 1 more generator until we add all the generators to find the best solution. Okay, this is the logic. So first, if we use the generator 1 and generator 2 to support the load, we have expression like this. If the generator 2 support P2, and then the generator 1 will be support D plus P2. Okay, because P1 plus P2, when we want to support total load equals D. Okay, so for this part, we just input-output curve for generator 1. We just copy this and this Okay. So for generator, if generator 1 support a total load of 50, the fuel cost 810, 75, 1355. Okay, we just copy this. Okay, this two columns here. Okay, you will find that for generator 1, 50, 810. Okay, this is the input output curve for generator 1. We also copy the data for generator 2. Copy the for generator 2. This is the power. This is the fuel cost. Okay. When 50, 750. Okay. When 50, 750. When 75, 1155. Okay. So this is for generator 2. Okay. This is for generator 1. Okay. Okay. So let's show you how to get this value. Okay. First, okay, for this element, that means we want to support a total load of 50, and the generator 2 support 50. Okay, so how much is left for generator 1? Will be 50 minus 50, so 0. So, and what's the cost for generator 1 if the power is 0? Of course, you found that when P1 is 0, the fuel cost is infinite. So for this element, that means F1 P1 plus F2 P2. P1 is 0. This is infinite. This part is 750. So the summation is infinite. Okay. So for this element is infinite. Okay. Similarly, we can cut the other element in this row. That means we have to support a total load of 50. If the generator 2 output 75 is impossible. 100 also impossible. 50 minus 100 will negative 50. That means the negative 50 is left for generator 1. It's impossible. So we calculate this impossible. Okay. Similarly, for second row. Okay. For second row. Then for the third row, that means we have to support the total load of 100, and generator 2 is 50. So how much is left for generator 1? P1 equals 50. Okay. When P1 is 50, what's the cost for generator 1? Is this number. Okay. 810. P1 equals 50. The cost is 810. For P2 equals 50, that means you see here, and the cost is this. So F1 plus F2 equals, okay, this is the number. That means this number, how do you calculate this number? This is the P2 because it's in this column. And how much is left for generator 1? Because the total load is 100, so 50 is left for generator 1. For generator, if generator 1 output 50, the fuel cost 810. So we got this number. Okay. So for this element, that means generator 2 output 75. So how much is left for generator 1? Generator 1 will be 25. 25 is impossible. You see, 25 is impossible because P2 is from 50 to 200. Okay. So that means the fuel cost for generator 1 is infinite. So infinite plus this number is infinite. Okay. Similar calculate the other. Okay. Next. Okay, we randomly choose a number. Okay, this one maybe. Okay. This number means P2 equals 75. Okay, because in this column P2 equals 75. The total load is 175. So 100 is left P1. When P1 equals 100, how much cost is for P1? Is this number? Okay. So This is for F1. Okay. For P2 75, the cost is F2 is. Okay. So for this number, when P2 output 75, P1 output 100, how much is the total cost? Of course, F1 plus F2. Okay, will be 2,650. Okay. Okay. So you should understand how to calculate this number. So you just use this procedures to calculate all these numbers. Okay. So you have all the results for this part. Okay. You have the data for this part. Okay. So let us talk more about this the meaning of this of each row. For example, for this row, what's the meaning of this row? That means you want to support total load of 200, but you have many choice. For this number, you choose to allocate generator 1 equals 50, and okay, I want to analyze this row. You can choose either random row. It's okay. First, we want to analyze the meaning of this number. Okay, that means P2 equals 50, and P1 equals 150 because 200 minus 5. That means this cost is for P2 equals 50, P1 equals 150, and the cost is this. For this number means that P2 equals 75, P1 equals 125. Okay. For this means P2 equals 100 and P1 equals 100. Okay. The fuel cost is this. This means P2 equals 125 and P1 equals 75. Okay. This fuel cost is for P2 equals 150, P1 equals 50. Okay. Because this row is for total load of 200. Okay. So that means for this row is to support a total load of 200, but you can choose different options. For this, you choose to generate P2 by 50, P1 by 150. For this number, you choose to generate P2 by 75, P1 by 125. So based on this result, you can got a conclusion that if you want to support a total load of 200, what's the most economic way to support the 200? Of course, you should choose the minimum value based on this rule. So of course is this. That means you want to support a total load of 200. The most economic way is to support P2 by 150 and P1 by 150. So for each row, we just record the best solution here. The best solution to support 200 total load is the fuel cost is 2,760 and the output of P2 is 150. Of course, you know how much is P1. Of course, it's 50 because the total load is for this row is 200. Okay. Similar, we choose this number. What's the meaning of this? It's very simple. You should find the minimum value in this row. The minimum value the value in this row means you have to support total load of 125. And the best solution is P2 equals 75 and P1 125 minus 75. So P1 will be 50. Okay. So the number in this column means that if you want to support a certain total load, what's the best solution, best fuel cost, and also what's the specific output for P1 and P2. Okay. So can you follow me? Yeah. Any question for this table?
No, sir.
Okay. Okay. It's very simple. I mean, you should calculate this table based on the input output curve of P1 and P2. Okay, you have many solutions. Okay, you have many solutions to support total load of 200. For example, 1 solution, 2 solutions, 3, 4, 5 solution, and you found the best solution is this. The best solution is P2 equals 150, and P1 is 50 because you use 200 minus 150 is 50, and the cost is this. Okay, so to support total load of 200, the best solution is 2070-60, and the best output for P2 is 150 and 50 for P1. Okay, so that means to support total load of 100 by P1 and P2, the optimal solution is this. To support total load of 125, the best solution is this. To support 150, the best solution is this. To support 175, the best solution is this. Okay, so we got. So we continue. We can calculate this table. Okay, calculate this table. Okay. So based on this table, we have got the solution for to economically support the load if from 50 to 350. Okay, so so that means that if you want to support a certain load, you can just look up the solution based on this table. Okay, however, this table is only for 2 generators. Okay, 2 generators or 2 units. This solution is only for two units to support a certain load. You see, our problem is there are 3 generators. 3 generators. So based on table, we should continue to add another generator. Okay, so let's continue. The table is only for 2 generators. You see P1, P2. So next we have to add another generator, generator 3, to this table. So the minimum cost for scanning unit 1, unit 2, and unit 3 is this. If unit 3 is support P3, and the left for generator 1 and generator 2, this means P1 plus P2. Okay, equals D minus 3. Okay, that means there are 2 generators. Okay, so if let P3 covers all allowable range for the demand, here, this data, how do you got this data? Actually, this data is just the result from here. Just result from here, you see. That means to support the total load of 100, the best solution is this. 125, the best solution is this. This is for 2 generators. Okay, we copy the data from here to here. Okay, when the support total load of 100, by 2 generators, the fuel cost is 1,560. Okay. Okay, 150. And when you support total load of 125, the best cost is 1,965. Okay, for the second, third, fourth. Okay, you just repeat this data here. Okay, what's the meaning of this? That means you use 2 generators P1 plus P2 to support this load. To support this load, what's the fuel cost? Best fuel cost. Okay. Similarly, we copy the data for generator 3 here. For generator 3. Okay, this is for generator 3. Similarly, for this element, that means P3 equals 55, and total load is 100. So how much is left for P1 plus P2? It's only left 50 because D minus 100 minus 50 because P3 is 50. So P1 plus P2 is 50. P1 plus P2 is 50 is infinite because you know 50 infinite. Okay. Total load 50 infinite. Okay. So similarly, we can count the element in this row. Similarly, is also impossible for this row. Okay. Next, I calculate this. This means the generator 3's output 50. How much is left for P1 and P2? The total load is 150. So P1 plus P2 equals 100. When P1 plus P2 equals 100, what's the best cost for this? Is this? Okay. 1,565 and 560, and P3 equals 50. Their fuel cost is 806. So the total summation is 663, 2,366. So this is the number. So we calculate the number very similarly in this table. We just allocate 50 to generator 3, and the left is located between generator 1 and generator 2. For this row, the total load is 150. If you give 50 to P3, and the left is 100 for P1 and P2. For 100, the best fuel cost is 1,560. Okay, continue for the other elements. Okay. Similarly, you calculate all other elements. Let us randomly choose a number. Okay, maybe this way. Okay. What's the meaning of this number? The meaning of this number is you have to support total load of 275, and you give P3 100. Okay. How much is left for P1 and P2? Of course, 275 minus 100 will be, yeah, P1 plus P2 equals 175. Okay. The fuel cost for this,
2465.
Yeah, 24. Yes, very good.
65.
This way. Okay. For P3 equals, for this number, when equals 100, the F3.
1411.
Yeah, 1411. So you add this number together. Yes, you will got this. 300, 800. Yeah, 76. Yes. Yeah. So you should know how to calculate this number. Okay. Okay. Any question for this? I think it's very, to calculate this table is very similar like this, but you should know what's the meaning of each number or how to calculate the number. For this number means you fix P3 as this value, and the left is for P1 and P2. Okay, for this is 275 and minus this. That means this number is 200 for P1 and P2. Okay, 200 for P1 and P2. So this fuel cost plus this cost, you will got this cost. Okay. So it's very easy to calculate all these numbers, and and for this part. Okay. So very similar way, we want to find the best solution to serve a total load. Okay. So based on this rule, for each row, what's the meaning of each row? This rule means that you have a support load of 200, and you have different options. Yes. Option 1, option 2, option 3, option 4, option 5, option 6. That means you have to support the total load of 200 by generator 1, generator 2, and generator 3. You have different options. Different options have different fuel cost. Which is the best? Of course, you will choose the minimum value is the best cost. Okay, what's the best solution? This best solution means P3 equals 100. So P1 plus P2 equals 100. Yes. So that means to support total load of 200, the best fuel cost is 2,979, and P3 is 100, and P1 plus P2, sorry. If you add another column here, you mean that P1 plus P2 also 100 because the total load is 200 and generator 3 fixed at 100, so the left is 100 for P1 and P2. Okay. If you want to find the solution P1 and P2, you know that for total load of 100, the best solution is this. What's this? It means that generator P2 equals 50. Okay. Generator P2 equals 50. And P1, of course, also 50. Okay, for this solution means that P2 equals 50 and P1 also equals 50. Okay. Okay. Okay, let's choose another row for this row. Okay. This row, what's the meaning of this row? The number in this row means that you have a support a total load of 325, and you have different options. 1, 2, 3, 4, 5, 6. You have 6 options. For option 1, you have your full cost of this. Option 2, option 3, option 5, 4, option 5, option 6. And what's the best option? Of course, you want to minimize the fuel cost, so this is the best option. What's the solution for this best option? The solution is P3 equals 150. So how much is left for generator 1 and generator 2? Of course, is 175. You just use this minus this. So that means here P1 plus P2 equals 175. This is the best solution. Okay, based on this, we can continue to look up the table. For total load of 175, you see 175. What's the best solution for generator 1 and generator 2? You know, is this value.
2465.
Yeah, 2465. What's the solution for P1 and P2? You see, P2 is 125. Of course, P1 will be 50. Okay. So that means for this number, P3 is this. P2 is 125. Okay. 125. And P1 is this minus this, so 50. So for this solution, the best solution, the best fuel cost will be this, and the fuel cost and the generator 3 is 150, P2 is 125, P1 is 50. Okay, this is the best solution. So that means if you have to support the total load of 325, the best solution is P3 equals 150, P2 equals 125, P1 equals 50. Okay, this is the solution. Okay. Similarly, you can find the total load for other node levels. For example, for 375, the best solution will be this. The best solution is P3 equals 150. Okay, and P1 plus P2 equals 225. Okay, and then you return back to find the table. Okay, this. Okay, so okay, please.
Silly generators, the power demand was 310 megawatt.
For which row?
No, before. The total demand.
Okay, before, yes. This table?
Yeah, no. Again.
This?
No.
Okay, please.
The power demand was 310.
300. This one. Okay.
No. At the beginning of the question.
At the start of question, the demand was given. He is asking for that.
Yes.
Without finish our problem, you will find that we have to continue. Yeah. Okay. Without finish. Yeah. until now we only have some possible solution for certain node levels. For example, 100, 125, 300, 325. Yeah. I know our question is to support the 310. Not this one or this one. We have to continue.
Oh,
okay.
very good.
Okay. So based on this table, we have found the best solution for certain node to support by 3 generators. Okay. As you said, our problem is to support total of 310. So it doesn't exactly match this number. So we have to continue. Okay. How to continue? So based on this 300, you found that the best solution is 4,168, and the best solution is P3 150, and P1 plus P2 is 150. 150. Then P2 equals 100, and P1 equals 50. Okay. Yeah. Sorry, this should be P3. Here be P1. Okay. You see, for 300, this is the best solution. For this is P3 fixed at 150. Okay. So fixed at 150. And the left for this number is 300 minus this will be P1 plus P2 will be 150. Okay. Means that P1 plus P2 equals 300 minus 150 equals 150. Okay. What's the best solution to support the total load of 150? By 2 generators, we should look up this table. To support total load of 150 by 2 generators, this is the best solution. Okay. This is the best solution. Then you can look up the table, found P2 equals 100. Okay. Of course, P1 will be 50. Yes. Because total load is 150 minus P2 equals 100. So the left is 50 for P1. Okay. So for 300 total load by 3 generators, you fix P3 as this, and P2 100 and P1 50. Okay. Do you understand this step? We first look up table for P3 based on this table, and further for P1 and P2 equals 150, we should find the best solution for 2 generators to support the total load of 150 based on this table. Then you will find P2 equals this, and P1 equals 50. Okay. So similarly for 325, because our load is total load is 310, it's between this number. Yeah. So we should find the nearest two number to find some and to do some interpolation or extrapolation for this number. Okay. So for 325, for this rule, the best solution is 4,463. So for P3 is also 155. For P1 plus P2 is 175. Okay, this number means P1 plus P2. We just use this minus this, so 100. So 175. 175. We then look up this table for 2 generators. 175. The best solution is P2 equals 125 and P1 is 50. Use this number minus this. Okay. So P1 equals 50. You see, P1 equals 50. P2 this one. P3. Okay. So based on this, can you give me some observations? Of course, for 300, P3 150, P2 100, P1 100, P1 50. For this 325, the P3 150, P2 125, P1 50. So that means for this 25, for this increase 25 megawatt, you only have to choose P2. Yes, P1 and P3 is kept constant. You have to choose, you have to change P2 to support the 25 megawatt. So our question is, if you increase 10 megawatt, which generator should support this? Of course, also should be P2. Because you increase from 1, because you increase 25 megawatt, this 25 megawatt supported by P2. If you increase from 300 to 310, that means you increase 10 megawatt. This 10 megawatt, of course, should be supported by P2. Okay. So generator 2 is the marginal unit. That means it pick up all the additional demand increase between 300 and 325. Okay. P1 50, P2 111, P3 100. Okay. Then the total load is this. Okay. Do you understand this? Because based on this observations, we found that P2 increased 25 to support a total load to support an increase of total load 25. So if you increase total load of 10, of course P2 will increase 10 from 100 to 110 to support this load. Okay. So the cost is easily determined using interpolation only for P2. Only for P2. We know that for generator P2, when the cost is 100, how much is this one? You see, for 100 is this one. For 125 is this one. Okay. Oh, sorry. For 125 is this one. So how do you calculate the value 111? What's the cost? It's very easy. Calculate like this. You just use the increment cost divided by the increment power, multiply the increment power, and plus this. This is the fuel cost for this number. Okay. So that means for generator 2, the cost is this. How much? This is generator 2. How much is for generator 1? You can just look up to the 50. The output is the power is 50. 50, of course, the number is this. Okay. So for F1 is this. For F3, 150. 150. 150 for 3 is this. Okay. So for F3. So the total cost will be this plus this. Okay, this will be this number. Okay, so we have used the economic dispatch to solve this problem. Let's repeat how to solve this problem. First, we have to calculate a certain load to economic support by 2 generators. We supported by P1 and P2. We got a table. Based on this table, we have the best solution for different load levels. For example, for 100, we have this best solution. For 225, we have this best solution. Then, based on the best solution for 2 generators, we add another generator 3 to form this table. This is for 2 generators. We add another generators, and we got the result. And finally, we got the optimal solution for 3 generators. Based on this, we can easily find the optimal solution for certain load levels supported by 3 generators. Okay. Furthermore, if you have 4 generators, 5 generators, you can continue like this until you finish all the generators. Okay. Okay, so any problem for this part? I think it's very easy for this. And next is how to allocate this 10 megawatt. How to allocate it? After analysis, we found that this 10 megawatt should be taken up by generator 2. Okay. Then we calculate the fuel cost only for generator 2 for this 110 megawatt. Okay, we got this. This plus fuel cost for generator 1 plus fuel cost for generator 3, we got the total cost. Okay. Okay, let's continue. And for economic dispatch, we didn't consider the ramp rate constraints. Actually, in practice, the generators have some ramp up or climb down limits. So that's the ramp rate constraints. So generators are usually under automatic generator control. A small change in load and a new dispatch causes the AGC to change the output of certain units. Generator must be able to move to the new generation value with a short period of time. That's the ramp rate. That means the generator's output can be adjusted very fast if the ramp rate is large. Okay, so large steam units have a maximum rate limit. That means in per unit value, in a per unit time, how much the power can be changed for the generator. So this is time. This is the change of power, or this is the power judgment. So this is the ramp rate. That means for per unit, per minute, or per hour, how much the power can be changed. This is the ramp rate. Okay. The AGC must allocate the change in generation to other units, and so the load can be accommodated quickly enough. In previous economic dispatch, we not consider this. You'll see we only consider the minimum and maximum range. Yeah, we not consider the ramp rate. Okay. So the new dispatch may be at the most economic values, but the control action may not be acceptable if the ramp rate for any other units are valid. That means if you change from T to T plus 1, for example, this is P1, this P1 plus delta P1. If this delta P1 is too large, maybe it's not satisfy this constraint, then the solution is impossible, because you can't change delta P so large in a short time period, for example, 1 minute. This is the ramp rate, means that you can't change delta P too quickly in a very short time. So what's the meaning of this? Okay. So to produce an acceptable dispatch to the control system, the ramp rate limits are added to the economic dispatch formulation. Then we require a short range load forecast to determine the most likely load and load ramping requirement of the units. So this we suggest suppose there are n total generators, and the load is P load T. This T is for that for different time period the load is different. And also we want to consider the ramp rates, so there are much time slots. We assume from T from 1 to T max. Okay, maybe 1 for clock for hour 1, 2 for hour 2, and something just like this. Okay, so each unit must obey a rate limit such that this means the next time slot equals the previous time slot plus this ramp rate. The ramp rate should in a limit larger than the minimum and smaller than maximum. This means to reduce PI, and this means to increase PI. Okay. So our objective is like this. We want to minimize n total load generators fuel cost in T max time slots. So okay, it's much complicated than the economic dispatch. Okay, here we add another index for T from 1 to T max. Okay. Also, for each time plot T from 1 to T max, we have the load balance constraint. total generation equals total load. Also, we have the ramp limit constraint. Okay, ramp limit constraint, and the next and the power output at t plus 1 equals power at t plus ramp rate. Okay, this is a more complicated economic dispatch problem. We not only consider this part. We have considered much time slots, and we also consider the ramp rate between different time slots. Okay. This kind of problem can be also solved with dynamic programming. Okay, you can code this program based on what we have learned for the simple economic dispatch in this class. Okay, any question for this part? That means before this we have solved some we have solved economic dispatch for different kind of algorithm. For example, the derivative-based methods, including the gradient-based, the lambda iteration method, and Newton-Raphson method. In this class, we have learned another non-derivative-based method, dynamic programming. We show how to solve the economic dispatch by the dynamic programming problem. Okay, then we expand the economic dispatch problem to include the multiple time periods to make this problem a problem like this. Besides the load balance constraint, we also have the ramp rate limit constraint like this. Okay, this is the full expression for the economic dispatch problem. Okay. Okay, any question? Any question for this?
No, sir. No, sir.
Okay.
Yeah.
So if you don't have question, our class will end. Okay. Thank you.
Lao Shi,
Yeah, please.
one student asked in the chat earlier, what if all generators are changed?
What is follow generator changed? What's your meaning?
Yeah, generator 1, generator 2, and 3 all are changing. What will be the change?
Oh, I know what you meaning here. Yes.
Thank you.
Okay. If you found two generator change, you should compare. Let me see. For example, maybe you say you have a solution here. Yes, one is here, and one is here. Yes. Okay. So you should compare the two cases. One is supported by generator P2 and the other is supported by generator 1. Then you compare these two cases together to find this which is better. Okay. If you found two generator change, you should compare the two cases. Okay. Well, can you repeat again? What you are changing? As in your case, only P2 is changed. If three generator change, you should compare the three cases. That means you fix different generators to compare three cases, and you found which one is better. Okay, then. Okay, I mean that I have answered your question. I have answered this question. Okay, if you don't have any question, we will end our class.
Okay.
Okay.